Dr. Rajendra K. Bera is an eminent Indian scientist, academician, and philosopher known for his contributions to interdisciplinary studies. He has a background in physics and philosophy of science and has worked extensively in the areas related to artificial intelligence, epistemology, and the interface between science and technology. Dr. Bera has held various academic and leadership roles both in academia and industry. He is also recognized for his efforts to bridge the gap between scientific inquiry and philosophical understanding, often engaging philosophical implications of technological advancements. His writings and talks frequently explore the ethical dimensions of science and its impact on society. Please join me in welcoming Dr. Bera to the stage.
I'm Rajendra Bera. I hope you can hear me. My voice is a bit weak, but through the help of this microphone, I hope I'm audible to everybody. This is corporate notice which professionals are supposed to adhere to. This appears to be somewhat a different kind of a setting, but it is an unexpected honor to be invited to this IIIT Confluence. With great sincerity, I thank the organizers and offer my greetings to those assembled here. I come with a fairly heavy background in theoretical physics, even though I was trained to be an aeronautical engineer. Many of my inspirations have come from the world of physics. Here are two quotations I thought was very appropriate to preface my talk. Mathematics is a tool specially suited for dealing with abstract concepts of any kind, including social sciences, and there is no limit to its power in this field. What Paul Dirac, who won the Nobel Prize in his early 30s in physics, there is no limit to its power in this field, means there is no power. It is actually well beyond any language we use for communication. Science is beautiful when it makes simple explanations of phenomena or connections between different observations. And I suppose everybody has heard of Stephen Hawking. So this is what he said. This particular lecture actually relates to what Stephen Hawking said. We have just stepped into a new era in human civilization that will test our ability to evolve and survive on the basis of Darwin's theory of evolution of the species. The Industrial Revolution strengthened our environment and genes so much that together with human life expectancy, which was about 32 years in 1900, stood at about 71 by 2021. Today it is higher. I believe it is 77 today. The time seems ripe where advances in AI will create a phase transition where we, the Homo sapiens, will speciate to a new and super intelligent species. Indeed, we may initiate it ourselves. Many of us at our age, while still alive and kicking, we don't think of the fact that, like all other species before us, we are also a part of that continuing process. We are not going to be Homo sapiens forever. We are going to be something else. God knows when, but we are definitely going to be something else. So this lecture will provide a glimpse on certain subtle aspects of this belief, because it lies at the heart of creating artificial intelligence. Now, this is a fact which I don't hear from my friends who are working in AI. They seem to think that what is present today is what is going to be there tomorrow and day after and possibly forever. All of us here, I'm sure now, including geometry. He codified geometry and he assumed that everyone instinctively knew what was meant by a point, a straight line, and a circle. So here is a simple question. Do every 3 points not lying along a straight line support a plane? Those who want to say yes, raise your hands. Okay. You guys seem to be pretty sure. Yes or no? So, in fact, a fairly good number of people said yes. The answer is yes. In fact, more than half of the audience did not think those 3 points lie on a plane. The question is why? Have you forgotten your high school geometry? Look at the figure. Look at it like a stool. The 3 points on the stool, don't they lie on a plane? The legs are of different size. The seat of the stool is not parallel to the plane on which the 3 points lie. Okay? Most of the time your focus is on the seat of the stool and not on the legs of the stool. This is one of the fundamental things about the properties of space, three-dimensional space. Any 3 points not lying on a line, they define a plane. Other than this, what else? Yeah, the answer is yes, and the plane is unique with an orientation ID, a unique orientation ID. That is the normal to the plane. The normal to the plane can be coming out or it can be going in the opposite direction. That is the only ambiguity there. The direction is unique. Your teachers probably did not tell you that. Other than this, what else can you say about the 3 points in the universe where the laws of nature appear to indicate that space is homogeneous, all locations in space are alike, and isotropic, that is, all directions are alike. So the laws of nature do not change because I'm looking in that direction or in this direction. And all moments of time, past, present, and future, there is no distinction between the two. This is absolutely fundamental in physics and the laws of nature that we know, in the form that we know. You were taught this theorem that the internal angles of the triangle is equal to 180 degrees. And if I randomly ask somebody in the audience to prove it, I think you will hesitate to do so. But should you have? Should you have been taught differently? You are given a triangle with angles alpha, beta, theta. You make 2 more copies of it, you have 3 copies of it. You put them as a jigsaw puzzle. You put them as a jigsaw puzzle, as you see on the right. And can't you see that alpha plus beta plus theta is equal to 180 degrees? Can't a little baby understand this? Does it have to be proven in a class? Does it have to wait till you are 6 or 7 years old or 8 or 9 years old? A baby gives their baby a triangle Ask the baby to make two more pieces and put them together like that. Alpha, beta, gamma is equal to 182. What's so great about it? What's so great about the Pythagoras theorem, by the way? You were taught what is there on the left-hand side. Only, I believe, after I completed my high school, at that time the proof was very, very difficult. People suddenly remember algebra, that there are two sides to what you call a geometry. Geometry and algebra are two faces, like the head and tail of a coin. You look at this diagram, you see A to D is A plus B. So you have a square which is A plus B of length. You look at the brown part, those are right angle triangles. Right? A into B, there are four identical such triangles. They form a square, two squares actually, and it will be 2AB. Okay? What does the algebra say? It says A plus B whole square is equal to C squared plus 2AB. So if that thing, if A plus B whole square, and you have taken out minus 2AB, what remains is the tilted square in the middle. And that is, you can read the algebra there, and you can see that C squared is nothing but equal to A squared plus B squared. The proof that I was given when I was in high school was the most difficult proof, and we were a little scared that it would come up in the exams. Would a little child of yours at the age of 6 who knows how to put jigsaw puzzles together, would he or she have a difficult time? I think those of you who are parents should try these tricks. Geometry will look so enjoyable because it is a game. You can teach the rest of geometry. It's a cakewalk. There's nothing that you need to do. So, our arbitrarily chosen 3 points not only live on a unique plane, but they also belong to a unique circle. The 3 points are ABC on the diagram. Draw perpendicular bisectors this AB on the line AB, and the point over the bisectors meet is the center of the circle. You know they will meet at a point, and only one point. That's the center of the circle. Why? Because the green lines are all equal. That's the radius of the circle. Is that difficult to understand? Anyway, no. So they lie on a circle. Inside the circle, very amazing things happen. There is something called the Thales theorem, and there is something called the Pythagoras theorem. Thales theorem says, which is at the bottom, so you can see that AC squared is equal to A squared, AB squared plus DC squared. At least you remember the formula, even if you don't remember the derivation. The generalization says that if you take the points on the circumference the way they are, then if at that point the angle is theta, then at the center it will be 2 theta, no matter where the point is on the circle. This has very important implications when we talk about the laws of physics. There is an unusual isomorphism that, if you're not familiar with the word isomorphism, what it means is identical. An unusual isomorphism, A squared is equal to AB squared plus BC squared, doesn't it suspiciously look like something that you have learned in physics as a fundamental law of nature? And that is, nature conserves energy. Since the time the universe was created, it was created with a certain amount of energy, and no change has happened to that. The total energy remains the same, but the energy changes form. And it changes form in two important ways. One is the potential energy, and the other one is the kinetic energy. I did my BTech from IIT-Bangalore. I'm not trying to boast about it. What I feel sad about the whole thing is that I learned this very fundamental part of theoretical physics after I did my PhD. It says much about the education system in the country than about the student. On the other hand, they never told you that it can be related to the Pythagoras theorem. Just by using trivial mathematics, you can say that it doesn't say it suspiciously look like total energy is equal to potential energy, where if t, square root of t is AC, square root of p is AB, and square root of k is BC, then the Pythagoras theorem is the template for the law of nature. And this template is such a strong template that I was just explaining to one of your students here that there is no law of theoretical physics in classical physics that can even dare to violate Pythagoras' theorem. Every law of nature can be recast into a Pythagoras' theorem. So while the lines A, B, B, C, AC represent abstract things, by the way, what is the square root of energy? You have no idea. You only have a mathematical idea of what we mean by square root of energy. We know what energy is, we can measure it. You cannot measure square root of energy. And that is where all the problem lies. So while the lines A, B, B, C, AC represent abstract things, the squares sitting on them represent things that we can measure. For example, energy and mass. It took a genius like Albert Einstein to show that mass and energy are related, that is, E is equal to mc squared. We're seeing is the speed of light, but in an entirely different geometry that we call space-time. So, taking from Shakespeare, there are more things in heaven and earth, Horatio, than are dreamt of in your philosophy. You can translate this in terms of those without a background in science, in terms of, say, literature. Isn't it a profound statement that Shakespeare makes in one of his plays? A thought, if 3 points in three-dimensional space define a two-dimensional plane, does it follow that meaningful information inside a volume can be viewed on the surface enclosing the volume? Doesn't it look plausible? Surprisingly, the answer is yes. Because space is a homogeneous and isotropic, and time is homogeneous. I said, there is no unique point in the whole of the universe which you can say that this is the point and there is no replica of that point in space. The whole of the universe, there is no unique point, and that is the fundamental part of physics. Because space is homogeneous and isotropic, not only you do not know your location in the universe, you do not even know in which direction you are looking at. There is no reference direction. So how do we do business? If I know you, then I know where I am with respect to you. If I look at the clock, I know where I am in terms of the clock, where in time I am in space. Yeah? So, if somebody tells you I'm in search of truth, you can give him a smile and tell yourself, you'll never discover the truth. Nature never intended you to know the truth. This is not a part of our philosophy. Truth is not knowable. So when you go back, don't keep on searching for the truth. Surprisingly, the answer is yes, because space is. So a long time ago, mathematicians like Carl Friedrich Gauss and Stokes discovered these profound relationships. The whole of theoretical physics depends on them. I'm sure anybody who has done a BSc or an MSc or a BTech in engineering knows these formulas from mathematics and probably scared of them even now. That is a problem with the way we have been educated, because these are the two most important theorems in the whole of physics, not at all difficult to explain, but they contain the crux of the way the universe is layered. What goes on is no different. It seamlessly matches with the rest of the building, the rest of the city, the rest of the world, and the rest of the universe. Seamlessly it matches. And that is what these two theorems are telling you about. No philosophy ever tells you that. No religion has told you that. It says that in the first thing, the Gaussian theorem, their left side is a volume integral. So it says what goes on inside a volume is, you can know that by looking at the right-hand side, which is information not inside the volume, but information on the surface of the volume. That is why it can go seamlessly from one place to another. In the volume, that particular, you don't have to understand, just remember that there is a mathematical entity which every mathematician understands. So there is no problem of understanding here. It is related to another mathematical entity on the right-hand side. The left-hand side says that if you have this volume of space, what is going on here? I sitting on the periphery of that volume, I can guess what you're doing inside. There is an uncanny isomorphic relationship between these two theories and quantum cognition and novel theoretical direction for psychology, namely complementarity, which suggests that some physiological measures have to be made sequentially, and that the context generated by the first measure can influence responses to the next one, producing measurement order effects and superposition, which suggests that some psychological states cannot be defined with respect to definite values, but instead that all possible values within the superposition have some potential for being expressed. That is what people who invented or discovered quantum mechanics learned. Essentially, this is how we derive theorems and conjecture theories. So what else is there? There's still a lot to be said about 3 points in space. Should this bother you? Yes. Because when AI machines start discovering them, where will you be? I don't think there's anybody in the audience who doubts that someday in the future, machines will begin to discover things that humans have great difficulty in discovering. In fact, all this is being embedded in our Omega project, and that is the project that I'm heading at the moment, and they will be augmented by a new axiom system where Thales, Stokes theorems will be axioms and not theorems. To an AI machine deriving endless theories from primitive axioms and storing them is trivial. Designing algorithms that solve a problem by selecting a set of theorems and sequentially applying them to find one or more solutions algorithmically will require AI-assisted human intelligence of a high order. By the way, I believe this is at the cutting edge of AI, and I'm not aware of any group in the world which is doing it other than my own group. So my tentative steps in AI in the 1990s, when I got interested in AI, I asked myself, is intelligence mechanizable? I still don't know the answer, but I believe it is to a very large extent. I also believe that intelligence is an emergent property of a class of natural neural networks governed by mathematical laws, and that this intelligence depends heavily on one's ability to draw analogies, that is, draw isomorphisms or visualize isomorphisms. That is, in some sense, decide if x is equal to y. Do you remember your mathematics? Isn't that probably for more than 90% of the time, that is what you have been doing? Left-hand side is equal to the right-hand side. So I got a patent on something which I still believe outside of this patent. Some people are aware of this patent, and those who are not, they probably still think this is a problem which is too difficult to solve. Given input variables x1, x2, x3, and output variables x2, x3, x4, two different coders write two different programs to do exactly the same thing. To tell you that given this input, will I get this output? You might be doing a lot of other things in the program. This invention of mine, on which I had a patent which was expired recently, it says that if you have only assignment statements, a string of them, you can answer the question. I do not think many of you will be able to answer that question unless you actually work it out by hand, much less give me an algorithm which a computer can do. Okay? It tells you even which program contains superfluous instructions. From my perspective, a successful AI system should be able to build an axiomatic system that looks at vast amounts of data, and then comes the important part, categorize the data by doing a correlation analysis, creates a random set of examples, and detect common features among numbers of this random set, not the whole set, but a randomly selected set by you. Proposes a parsimonious set of actions and rules of inference that would reproduce the observed features and predict new features as theorems. It was with this goal that I began to develop methods that would detect equivalences in mathematics, where one is for evident to see if x is equal to y. So, what all of us learning mathematics have been doing is the right-hand side is equal to the left-hand side. That is the problem that I addressed. Can a machine do that for me? While doing so, I always kept in mind that it is possible to prove the consistency and that it is impossible This is related to one of the most famous theorems in mathematics called Gödel's theorem. It is impossible to prove the consistency and completeness of any axiomatic system to which Gödel's theorems apply. The limitations are the computing powers of a universal Turing machine and the limitations imposed by the postulates of quantum mechanics, and that information is physical and hence governed by the laws of physics. We have been led to believe that information is abstract. I worked for IBM for 10 years. And one of the things I learned from the works of one of the famous researchers of IBM, he enlightened the world what we will do someday. He enlightened the world that information is physical. It is not abstract. And because information is physical, it is physical because without the material, without matter, you cannot transmit or emit information. Information and matter are tied together. So your information theory cannot violate the theoretical laws of classical physics. In fact, even the laws of quantum mechanics. This is now hardly, I suppose, any AI person here knew about this or knows about it. If you do not know about this, then I can assure you with a great deal of certainty that no matter at what advanced stage of AI you are working on today, you're going to get nowhere, absolutely nowhere. Because you think you're looking at abstract things and you're forgetting that that abstract information must necessarily be connected to matter. You develop technology, you have to understand matter. Above all, I see AI as enabling the integration of multiple technologies so that in our endeavors we can constructively disrupt before being disrupted. Economic growth no longer means growth in employment. This is not what my parents had told me, this is not what I had believed in during my service career. I learned this devastating truth around the time I was to retire. And since that time, the people I mentored, I never let them forget this particular real aspect of their life. Ray Kurzweil forecasts that the future will provide opportunities of unparalleled human-machine synthesis. One is in which I can claim to have considerable amount of knowledge is molecular biology. Today, synthetic molecular biology is trying to do what we never thought God had intended us to be able to do. That is, create life in the laboratory. Today, we have come to a stage we can actually edit the DNA the way I edit my Word files, almost literally. That is where we are today. So unless you understand molecular biology, it is very, very unlikely that you will understand the relationship between abstract information and that information is physical in molecular biology. Ray Kurzweil forecasts that the future will provide opportunities of unparalleled human-machine synthesis. He says, 2029, 4 years from now, is a consistent date I have predicted for when AI will pass a valid Turing test and therefore achieve human levels of intelligence. I have set at the date 2045 for the singularity, which is when we will multiply our effective intelligence a billionfold by merging with the intelligence we have created. We are not today worried, and I'm not working on problems where I worry. Can I create a machine that can do a good part of my work? The question is the opposite today. If I suddenly make a machine which outwits me, then where will I be? It is not just about me being Bera. Where will I be? Practically the whole world, where will it be? How are you going to earn a living? Just tell me that. It is based on this law of accelerating isotropicity that says that fundamental measures of information technology follow predictable and exponential trajectories seemingly unaffected by dramatic socio-economic events such as war and peace and prosperity or recession, paralleling Moore's law in computer technology. It turns out that once a technology becomes de facto information technology, all our knowledge can be rewritten in terms of information technology. It comes under the grip of the law of accelerating returns because computer simulation of any technology is all about mathematics and computation. And I concur with this view. When I was a teenager, there were no cell phones, social media, and the ubiquitous electronic gizmos of today. We used our brains, made conjectures, and refuted them, and did lots of things our parents frowned upon. And guess what? Some of us were even rash enough to make the machines compete with our brains. And we thought we were doing a great job. We were doing extremely interesting things. So in 2020, I wrote a book chapter titled Synthetic Biology, Artificial Intelligence, and Quantum Computing. I'm perplexed by the enormous resources being directed towards natural language processing in solving problems. All of us know natural languages have a lot of ambiguities built in them. Intelligence tries to filter out ambiguities. So if you think you are going to build an AI system by doing some extraordinary piece of work using natural language processing, you are thoroughly mistaken. NL is overburdened with fallible, irrational, incoherent, inconsistent, and ambiguous comprehensible knowledge unworthy of emulation. They're obviously algorithmically uncomputable. If it is uncomputable, it cannot be computerized. Indeed, of seeking knowledge in garbage bins like ChatGPT does, gems can be found by asking, given the output, what spectrum of inputs would have produced it. Mathematics is our only language that can face this enormous AI challenge. A pattern in mathematics refers to relationships between things, not the things themselves. Abstract thinking in math requires intelligence, and it can be taught by a few like Galileo, Newton, Maxwell, Einstein, Planck, and so on and so forth. And there are rare examples. It is so rare that family names are rarely repeated. How many Einsteins have you heard of? How many Newtons have you heard of? How many Faradays have you heard of? Mathematics connects the world via isomorphism. We cannot deal with AI with yesterday's thinking. Steam behaves differently from water. We know that, but do we know its significance? Just as water from ice, we are operating at such a high levels of energy conversion to useful work. These are the various forms of energy. Remember, the universe, the amount of energy in the universe has remained constant. What you see is how energy is transforming itself from one form to another. Thermodynamically, we are operating at high temperatures. Without a protective coating of intelligence, we will be burned. Those who can use AI as a handmaiden will thrive. The whole thing is about seeing deeply into the inner workings and structure of space and time. As Bob Dylan would say, the answer, my friend, is blowing in the wind. The answer is blowing in the wind. So, my last slide. With the one dot, you create. With two, you connect. With three, you loop. Remember that the triangle is a loop. On a 2D plane, you align. Three-dimensional information gets captured in a two-dimensional plane. In 3D space, you build a universe. In space-time, you gather. You change from one state to another. So, thank you for the attention.
Thank you so much, sir, for that talk and for giving us so much insights about AI systems. May I please invite upon our CAO, Mr. Jagdish Patil, to felicitate you with